Hello everyone. In this video, I will try to my best to help you prepare for your FE exam for civil engineering in for this structural analysis section. Okay, if you look at the FE manual in your page 268, that's where the structural engineering section begin. But the first part is structural analysis. For the first part is the influence lines for beam and trusses. So if you look at the description there, it is given that what you need to consider, or what are the possible questions that or concept that you should be familiar with, is that if there's a movable set of loads that passes through the beam, what will be the maximum value of that effect? For a beam, we have reaction, shear force, and bending moment. And for a truss, we are interested to find only the bar force or the axial forces, which means that the maximum forces that caused by this movable set of loads. Okay, so my intention here is to help you prepare as you are preparing for your FE exam. What are the possible questions, or what are the possible variation that you may expect from this section? So that is my genuine hope, and I hope that it may give you confidence while preparing for this class. Okay. Here's the what could be the possible problem or possible question that you may expect from those section in your structural analysis. I'm not going to go in detail. I already upload a video for to work on influence line for a beam using Mueller-Breslow principle, but here I'm going to just share with you um, how to use the concept in for your exam. Okay, so mind that in your FE, their average expectation is that you should not spend more than 3 minutes per question. Again, not always true, but that is just a general expectation. So here in the objective of this uh, video is to help you how to use the concept and to get the answer for questions. Okay, so for the first part, uh, before you start your whenever you start solving problem, the first part is read the question, try to analyze and see what is asking from you. Okay, for the first part, it said for the beam below, so this is the given beam, and it what it want is the maximum upward reaction at support B. So I want the maximum reaction at support B due to a concentrated live load. Remember that live load means that it's not a permanent load. That means it can move. So now we need to make in order to know when the reaction at B will be maximum as the load is moving from A to D. Okay, so to know that, we have to use influence line. You can use trial and error method, which means that you can put your load, your 20 kilonewton here, 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 and then trying to do calculation. So like you put at A, do the calculation, put at B, do the calculation, put at in the middle, do the calculation, put at C, do the calculation, put at D, do the calculation. But that will take you a long time, because doing like 5 6 trial and error method is not the objective of your FE, because it tests your fundamental concept. So we have to use influence line. So for influence line, if you wanted to get a reaction at support B, remember that in influence line, all you have to do is right now the support B is restrained. It cannot move up. So in a Mueller-Breslow principle, the concept is you remove that constraint. So that means when you remove, now it will move, and you give a unit distance. Okay, so we'll just draw a beam again here. I'll name this as A, and this is B, this is C, and this is D. Okay, so now you will move the point B or the joint B by a unit distance. When you use Mueller-Breslow principle, the concept is you cannot move the support and A, and you cannot move the support D. That means support A and support B has to be staying at the same position. They cannot move sideways, or they cannot move in any direction. Okay, but D will be allowed to move sideways, but you'll see that influence line, for there's no we are not interested in finding the actual deformation or the side deformation for your beam. We are interested in shear, reaction, and moment. Okay, so we are not going to worry about the side deformation or actual deformation. And then for the hinge, a hinge, it can go up, it can go down, and also it can rotate. Okay, so the about hinge, it can go up, it can go down, it can rotate in both direction. So if that is the case, so we have to draw a straight line, because the concept of Mueller-Breslow principle, it says that if once you move this joint B up, the deflection of the beam will be the representation of your influence line. So in this case, we'll have to draw a straight line to 1. Okay, so now the concept is, what do? Do you have to come down, or do you go straight like this, or do you go up? In Mueller-Breslow principle, the joint B, you're not supposed to bend, or you're not supposed to break the joint B. It should maintain the continuity. So if it has to maintain the continuity, that means it has to maintain the same slope till it reach C. And joint C is a hinge. It can go up, it can go down, it can rotate. So it will go back to D. So this whole thing is your influence line for BY, and it is positive. Okay, which means that you if you put a load anywhere in the beam, you will see that by will always reacting upward. So that's what positive means, it will always react upward. So now we need to find what is this ordinate of your joint at C, or your point at C. So we'll use similar triangle. That is, we know that this is 8 meter, this is 4 meter. So if I need to find the height of C, then we'll be using triangle. H over C equal to over 12 is equal to 1 over 8, and HC will be equal to 1.5. So this point will be 1.5 meter. So that is the influence line due to a unit load. That's why we apply a unit distance, because it's a unit load. And now if we wanted to find what will be the maximum reaction at B due to this life load of 20 kilonewton, all we have to do is we just need to put 20 kilonewton where the maximum coordinate is. So your maximum By, which is your upward, again positive, will be equal to P into Y of your influence maximum, and that will be equal to 20 into 1.5, which is at C, and that will give you 30 kilonewton. So that's how you find the maximum reaction for due to a concentrated life load of 20 kilonewton. So this is how you use the concept of influence line to get your maximum reaction at By. So you can also do your own calculation. You have this beam, you have all the support reaction, a support A, B, and D, and you apply 20 kilonewton at the hinge. And if you find what is the reaction, what is By in this case, you will see that your By will be 30 kilonewton using your skill in calculating the or finding the support reaction using equilibrium equation. Okay, so that is the first part that you may expect about influence line for a beam. What are the variation? Another variation that you can expect is for a beam below, you wanted to have a maximum upward reaction at support C. So now we are going to have a support C. Sorry, this is not support C, this is support, should be support D. Okay, we are interested in D. Now we are interested to find the reaction for the support D, and due to a uniformly distributed life load. Okay, so now it's not anymore a concentrated life load, but it will be a distributed life load. How do we use it? How do we find the maximum reaction at support D? Again, we use the same concept. We applying a unit distance, we release the restraint. Right now D is cannot move up, so we using Mueller-Breslow principle, it says that release that constraint in D and apply a unit distance, and then after that the deflection of the beam will be the representation of your influence line. So we are going to draw again the beam. This will be D, this will be C, this will be B, and this will be A. Again, we move a distance here, will fade 1 because that's a unit distance. And again, your C cannot move according to Mueller-Breslau principle. You cannot move the support up or down, but you can rotate the beam because support or roll support are allowed to rotate. And then B is hinge, it can go up or down, and A also cannot go up or down but can rotate. Okay, so now we have to draw. So if we have to draw the influence line, we have to draw a straight line, and then we have to maintain continuity. We cannot draw straight line over this because you can see that you're breaking or bending the beam at C, or you cannot go up because you're bending the beam at C. It's not allowed, and and it has to maintain continuity. So we draw another straight line, and then after that we draw the straight line at C. Okay, so your um, that will be your influence line for the beam. And so this will be positive and this will be negative. And again, the sign convention for positive means because we're applying a load what, so that will be positive. That means dy will be upward, and negative means dy will be downward. And what we are interested to find the maximum upward reaction. So we'll be focusing only on the positive part. And because it is a UDL, uniformly distributed load, the way you apply the load is by putting the load over the area or region where you get your positive influence line. So C to D is where you get positive. So you're going to put that live load 15 kilonewton over that region CD where you have your CD where you have your positive upward direction. Okay, so positive means upward. So you're going to place your UDL along this region C to D such that dy will be positive. So now you can say maximum Cy upward will be equal to 15 kilonewton meter divided by area under that UDL in influence line. Okay, so now we are only interested in finding this area, and this is the area of a triangle. So we can find that this will be equal to 15 kilonewton per meter, and area will be half base into height. Okay, so that will give you 60 kilonewton. And because I maintain the unit consistent kilonewton and meter, so I know that my upward reaction will be force, or force will be kilonewton. Okay, so again, like I said, if you feel like I don't think so is going to be positive, it's going to be 60, just use your equilibrium equation and find what is dy in this case, and you'll see that your dy in this case will be exactly 60 kilonewton. So I've shown you a variation of one of using a unit load or a concentrated load and live load, and one is having a UDL live load. Okay, so that is the variation for reaction. Now you're going to see the variation for the negative shear force. How do we apply shear force in a beam due to a concentrated live load of 40 kilonewton? Okay, so in this case we are interested to find the shear force at joint C. The Mueller-Breslau principle of applying a shear force at joint C is by you're going to rotate or move up the beam CB, and you're going to move down the beam AC or the section AC. And this is a sign convention for a positive sign convention that we follow in Mueller-Breslau principle. And if this is your distance A, which is 3 meter, and this is your distance B, then you will be applying b over a plus b upward, and you're going to apply a over a plus b downward. And that's what we're going to do. Okay, so we are going to draw again another beam, and then we put here b, here c, here a. Again, a we cannot move, c we cannot move, and now we are going to rotate the section AC. Can we rotate this section AC downward? Yes, because this is a hinge. Hinge is allowed to rotate, so we are going to draw a straight line AC, and that value will be calling us minus a because it's going downward. So this will be your negative area, minus a over a plus b. So that will be minus 3 divided by 6 plus 3, and that will give you minus over 3. And then for the b part, we're going to draw a straight line, but again, we we have to make sure that it's continuous, or the continuity is maintained, and we cannot bend or break the beam at a joint B. So that means it's going to be a straight line. And so this part will be b over a plus b, which is 6 over 9, and that will be equal to 2 over 3. And for this part, we're going to use let's call this part as d. So we're going to use similar triangle. HD over 3 is equal to 2 over 3 divided by 6, and you'll see that your HD will be equal to 1 over 3, and so this part is 1 over 3. And you'll see that this is negative, this is positive shear. So you have negative shear and you have positive shear, and what it's asking is asking for a maximum negative shear at point C. So because we're only interested in negative and they are a live load, that means they are not a permanent load, so you can put the load only at the region where it's positive. So you put a load here and here, so which means that you load UDL load over section AC and BD. So now if you say maximum shear force at C, -1 will be equal to 40 into the area minus half into 3 into 1 over 3 plus 40 into half, because there are two area, 3 into 1 over 3, and this also will be negative value because they are in the negative region. And so if you do the calculation, you'll see that this will be equal to 40 kilonewton. So maximum shear force at C for negative shear will be equal to minus 40. Okay, you can do the equilibrium equation and find the shear force at C for negative value, and you'll find that it's going to be minus 40. Okay, so that is how we use the concept of influence line to find the reaction, to find the shear force, and now we're going to do for a moment. Okay, so for moment, we are interested to find a moment at C, and you'll see that the maximum positive moment, remember it's positive moment at C, okay, due to a live load and a distributed load. Now we have not just a live load, but also we have a dead load. Remember that dead load is a permanent load, so that means that load has to be applied all over the all over the section of the beam, not just a positive or negative part. Live load, yes, you can put only in a section that you are interested, but that load has to be all over the section. Okay, so for drawing the principle, drawing the moment for at joint C using Breslow principle is you're going to rotate this beam CB, and you're going to rotate this beam AB in this direction, and your total theta, which is your total rotation, will be 1 radian. Okay. So if we do that, remember that this is theta 1 and this is theta 2, so which means that theta 1 plus theta 2 has to be equal to a unit radian. And so we'll draw again the beam, and again joint A cannot move, joint B cannot move. But we know that AC we can rotate. Why? Because it is a pin, so it will rotate counterclockwise at C. This is your point C, this is point, this is A, this is C, this is B. So we're going to rotate in your um, clockwise, or sorry, counterclockwise for AC, because that's the rotation we want. And then for BC is going to be a clockwise, so that's the rotation we want. Okay, so this joint C, or ordinate of C, will be equal to A B over A plus B. If this is your A and this is your B, then it'll be AB divided by A plus B, and this will be equal to 2. And for this part, using again similar triangle, you equal to 1.5. So this will be your positive moment and this will be your negative moment. Okay, so now how going to apply the load? You are going to apply the load by UDL for the dead load 60 kilonewton per meter all over the area, or all over the length, because that is a dead load and it's a permanent load, so you cannot place it only in the region of interest. However, uh, for the live load, you'll place only in the positive, because we are interested to find a positive moment. So you're going to load live load only in the section from A to B, because that's the region where we get a positive. So this will be 40 kilonewton per meter, which is your live load, and this is your dead load. So we already know how to find the maximum, so we're going to say maximum moment at C due to dead load will be equal to 60 into half base into height plus 60 into, remember that this section has a negative area, so it will be negative into 3 into 1.5. And if you do the calculation, you will get 345 kilonewton meter, because we maintain the unit kilonewton and meter, so we know that it's going to be kilonewton meter. And then maximum moment at C due to live load will be equal to 40 into half base into height, which is equal to 320 kilonewton meter. And for your total maximum MC positive, remember that this is positive 1, so it's going to be 320 plus 345, and that will give you 665 kilonewton meter. So which means that if you put the load exactly as position the load exactly as given here, you'll see that the moment at C will be 665 kilonewton meter, and that will be your maximum moment at C. If you put your load somewhere else, it will never cross 665. So that is what is expected from your FE manual for your uh, this section of your structural analysis for beam. Again, so that is what is needed for the influence line for a beam. So I've covered for how to do with a reaction support, what to do with the unit load or concentrated load, what to do with the UDL load, and then what to do for shear and for UDL, and then what to do for a moment if you have dead load and live load. Okay, so those are the uh, concepts that's required for the influence line for a beam. And you can see that any question they ask, as long as you are clear with how to use Mueller-Bresser law principle and how to use the load from your influence line diagram, you should be fine.